greeting. So we're continuing our discussion of how Archimedes made his calculations to arrive at an estimate of pi. And we're now looking at the internal, or the inscribed figures. And you remember this diagram from the previous video. And we began with a 30-60-90 triangle, where 30 degrees is over here at vertex A, namely the angle CAB is 30 degrees. B is a right angle because it is an inscribed angle sitting on a diameter. And so this must be our 60 degrees is at vertex C in this diagram. So that's going to enable me to then tell myself, hey, I know what some of these measurements are. A to C is going to have a value of 2. A to B is a value of square root of 3. AC is a value, BC is a value of 1. And then we're going to do the same thing we did a moment ago, where we're going to now start trying to figure out these bits and pieces over here. And I'm mainly going to figure out the length of BN. And I'm going to figure out the length of BN just as we did earlier. So now what I need to do, though, is get this into my spreadsheet. And so I'm going to use the same spreadsheet I have here. I'm going to step down so that I can basically build my other side of the equation, as it were. And I'm going to have, as I said, AC, we're going to have A to B, and we're going to have B to C. And according to that diagram, AC is 2. A to B is where we're going to get the square root of 3. What Archimedes had to figure out with a fraction. Still blows my mind that he could do that. And then we have BC as 1. Now the next thing we're going to calculate is BN. Let's go back and look at our diagram. If I get BN, then the very next thing I'm going to get is CN. Alright, so I know in my spreadsheet I have BN, then I calculate CN. Back to my diagram. So now I have all of the outside bits calculated. The question is now I need to get A to N. And I'm going to do that because it's part of a right triangle. ABN is a right triangle, and I now know the length of A to B and the length of B to N. So now A to N will be determined. So this is going to be AN is next. Now the reason I want AN next is because now I need to get the value from C to E. And I'm going to do that, if you remember, by having similar triangles. And so I'm going to put an equation over here relating the pieces I wish to relate. I know that the length from C to N in this triangle, I have, let me not do CN, I want C to E as a numerator, and my denominator will be C to N. And that is going to be equal to another ratio, and this ratio is now going to be in triangle ABN. And so if I look at this, I know CE is opposite this angle ENC, so the side opposite this angle BNA, or AB is what I'm looking for. So AB, and then it's going to be over, and I see that this is going to be the length from C to N. Well, that's going to have to relate to A to N, which is why I needed that measurement. So using that arithmetic, I know that CE, the value I'm looking for, is going to be AB, known, times CN, known, then divided by A to N, a known value. So the next piece in my puzzle over here is C to E. Now after I get there, we're going to be able to calculate a parameter. And after we get a parameter, we're going to do just like we did before, where we're going to divide parameter parameter by the diameter. And so we understand what our calculations are. We're just going to try to fill these in now. So let's see if we can do the arithmetic. Bn, well, that's going to be very similar to the calculations we had earlier. I'll let you fill in the missing bits. I'm simply going to come over here and begin typing my values. Bn is going to be equal to a ratio, and it's going to be AB times C to B, and then we're going to divide that by the sum of AC plus A to B. So there's my value of Bn. Cn, if you will remember, is going to be the length from B to C minus the length Bn, which we just calculated. An is going to come from our right triangle, so that's going to be the square root of, and we're looking at the square root of A to B, quantity squared, plus B to N, quantity squared. And so there's my value of A to N. And then last but not least, CE is equal to Cn times A to B divided by An. And this is going to pretty much give us what we need to know. Now, before I get carried away, we began with the length of C to B as part of my hexagon. Now notice C to B is not half of the side of the hexagon. It is the whole side of the hexagon. So I'm not going to need to multiply the distance from B to C by 2. I simply need to multiply it by the number of sides. So when I'm looking for the perimeter, I'm going to take BC and we're going to multiply it by the number of sides. And then so, to get the diameter, this ratio of diameter, we're going to take perimeter divided by, let's look at our diagram. Our diameter is the length A to C. Alright, so I'm going to divide by A to C, and lo and behold, we get a perimeter to diameter ratio of 3. Alright, but now, how do we update our information? This is the part that we really need to think about. So, what's going to happen is my A to B needs to be replaced now with my A to E. So I'm going to bring this up. So my A to B now needs to be what I find A to E to be, but notice I don't have an A to E calculated here. Whoopsie-daisy. Alright, no fear, hang on. So we're going to need, we know we have A to N, we just need to calculate this little bitty piece right here in order to get the rest of the puzzle. Not a problem. A to C is going to stay A to C, and what was B to C is going to become C to E. So C to B is going to become our C to E. And we said that AC stays the same. So the only piece of this puzzle we're missing then is this update, and we need one more little piece of information. So let's go over here and take a look at how we're going to determine this. Well, remember we have this triangle, and we know we have similar triangles. So I'm going to use similar triangles one more time, and I'm going to be able to make the following statement. That N to E, let me put my fraction symbol in first. Alright, so we're going to do N to E, because that's the piece I'm looking for. is going to be over n to c. I can pick any other part of this triangle I want, but I'm going to do n to c is going to be equal to, and remember we're relating to this big triangle up here, so let's put our sides in. And we have this little bit of side, so that must be my b to n. And that is going to be, let's see, we did this side right here, which was a long side, which is going to be my a to n. So we now know that n to e is going to be equal to mc times bn divided by an. So I'm writing this down, and that way I'm going to be able to do some calculations in my spreadsheet, and we'll be able to be on our way tickety-boo. So let's come over here, and I know I'm looking for ME, and we said that ME is going to be equal to N to C times B to N divided by A to N. Alright, so here's my ME. Now, the problem is, if we think about what this gives us, I need to take my AN and my ME, and that's going to be, when I add those together, becomes my new A to B. Because I'm letting this new triangle here be represented by this one before. We're going to do the same thing over. So, my new A to B is going to be equal to my A to N plus the little bit N on to E. And because of that, I can now calculate yet another iteration. And somewhere we got some zeros. Let's see where things went up down the line. Oh, I'm going to tell you how many sides I have. This is going to be 2 times the number of sides we had previously. And notice our ratio is now up to 3.105. And I should be able to update my new ME, and it's getting shorter. And what I want to do now is simply pull this down until we get to minus 6 sides. And notice my value for pi is 3.141032. And you can compare that to the value above. And what I'm going to do is I'm going to talk about the difference of these two numbers. I'm going to take the larger minus the smaller. So larger minus the smaller. And notice our error is not in the tenths, the hundredths. It is 1/1000ths. It is 16 ten-thousandths away from the real value. I'm sorry, those two values are apart by 16 parts out of 10,000. That is a very, very close estimate. So Archimedes, very early on, was able to give us a very good estimate for what is pi. I'm pretty sure that Archimedes knew that he was very close. And I'm pretty certain that he probably stopped where he did because A, for all practical purposes, he has nailed the value of pi close enough for any scientist of his day to do whatever calculations they need. And secondly, his limitation having to deal with fractions and make guesses at what these ratios would be, I think we're starting to get very limited. As I say, come down and look at the works of Archimedes translated by Heath, and you can see we're talking about 5 and 6 digit numerators and denominators that he's using as ratios. And I think it just got to be a bit too laborious, and he just didn't have the tools to get much closer. But this is how Archimedes got pi. And if you want to really try to nail this, I encourage you to rebuild this chart and basically go for some more sides and see what you come up with. This helps you understand how the ancients did some really impressive mathematics.